Hello, my name is Kevin Davis, and today I'll be doing my lab report for Lab 3, Black Hole and Orbits. To introduce the lab, part 1 of it will be observing the motion of a star orbiting around a black hole on GlowScript using the starter code, and then determining the mass of the black hole using the data. And then in part 2, we'll be finding the initial velocity of a spaceship for it to orbit but not crash into either the planet or the moon. The fundamental principles of physics demonstrated in this lab are Newton's second law, which says that the net force of an object is equal to dp, position, over dt of time. The momentum definition is that momentum equals mass times velocity. The parallel and perpendicular components of the net force, or dp over dt, is equal to the parallel or perpendicular components of dp over dt added together, combining into the net force. And then the gravitational force equation saying that net force is equal to negative g big M little m divided by r hat, the magnitude of r hat squared times r hat. In part 1, the system of the lab is the star and the surroundings are the black hole. The initial conditions is the change in time is 86,400 seconds, and the mass is 2 times 10 to the 30 kilograms. In the code here, you can see the seed is my email, cdavis427@georgiatech.edu. On the side with the code, it's talking about the initial and final velocities in line 157, 158. Then it's talking about the change in momentum, P equals mv. Then the next lines, delta v and delta p, are talking about the change in velocity and momentum. The next line is talking about Newton's second law, finding dp dt. Then it sets the net force equal to dp dt. Then the line after with p hat and d mag p dt is the parallel momentum. And then the line following is the net force of the parallel components. And then it's showing the parallel and perpendicular things added together in the next line. dp over dt equals dp divided by dt parallel plus dp divided by dt perpendicular. And then it's talking about the perpendicular net force. And then it's showing how to find big M with those given values. So these are the results of my orbit with my seed. I found the average mass of the black hole to be 9.89583 times 10 to the 33 kilograms. Found that by averaging all the numbers in Excel. For part 2 of the lab, the system is the spaceship in the moon that orbits the surroundings of the planet. The initial conditions are that the mass of the planet is 6 times 10 to the 24 kilograms. The mass of the moon is 7 times 10 to the 22 kilograms. The mass of the spaceship is 7 times 10 to the 12 kilograms, and the change in time is 30 seconds. Here is the code for that lab, for that part. So it is showing that the force of the moon by the planet, how to calculate it, the sum of the forces on the moon, the force on the ship by the planet, the sum of the forces on the ship, and then the updated velocities and positions of both the moon and the spaceship, as well as the initial conditions stated above, and I've covered the x and y speeds that I chose. So these are the results of it. It follows the planet at first on the outside, and then it goes under it and back around. After trial and error, I discovered that negative 80 is the correct speed vector for the x-axis, and that 50 worked well for the y-axis. Possible errors in this lab is that it doesn't represent a fully realistic situation, as there could be other outside forces affecting it, as well as there are multiple correct answers for this because of trial and error. So albeit my speeds worked for the orbit that I wanted and desired, another orbit could have occurred with different speed values that may have looked the same or different. The what ifs in this lab is talking about how I should discuss the net force and its parallel and perpendicular components and how they're different. So mathematically they are the same, as Fnet equals dp divided by dt. However, the Fnet requires knowing mass and distance, whereas dp dt is observing and measuring the changes in an object's position and velocity over time. The next question is, this imaginary system has a black hole, a star, a planet, and a moon. If you wanted to predict the motion of the moon, what would it be? So we'd have 12 different gravitational force vectors simultaneously that would not all contribute equally because of the dominant interaction by the black hole and its gravitational pull. Meanwhile, the tiny moon's pull on the black hole would be